So basically this course has few prerequisites, except it should not be your first course in control. Okay, so if you've never heard about feedback or whatever, you should probably take a course first, but it can certainly be your second course in control. Okay, you don't need to have any advanced knowledge of any advanced material in linear control or even nonlinear control. So basically, some just basic state space knowledge is enough. As you noticed, also this course is being recorded, which might make it a little weird at times, but we'll see. So the first half of this course is based on this outstanding textbook, and then the second half is more recent material. Any general questions? Also, you should feel free to ask questions. Even though it's recorded and so on, feel completely free to ask questions. It's if you've been listening, not looking at the New York Times on the internet, but if you've been listening and you haven't understood something, it's likely that half of the class hasn't understood it either. Okay, so you're really doing a favor to everybody by asking a question, by interrupting. Okay, so do feel free to interrupt and ask questions. So on the second page of your handouts, you have kind of a list of topics in nonlinear systems analysis, nonlinear design tools, adaptive control, estimation. So we're not going to go through them in detail now, but the course is very much oriented towards developing reasonably simple mathematical tools that can be directly applied to real problems. Okay? So some of the most arcane aspects of nonlinear control we may not cover. On the other hand, we'll try to cover well the parts which can be directly applied, at least some of the parts. So why nonlinear control? Well, from a practical point of view, all or most real systems are nonlinear, by which, if you can describe them by a differential equation or a discrete equation, that equation will be nonlinear. Okay? So for instance, if you think about a robot, okay, and you're just trying to write the dynamics of the robot, how the robot moves as a function of what kind of torques you apply to its joints, okay? Well, you have things like Lagrange equations, right? So they have sines and cosines and squares of velocities and things like that, right? And there's nothing to linearize the system about, right? You have to deal with them, right? If you're trying to do a precise motion in space, then you have to deal with these full nonlinearities, okay? Similarly, lots of chemical systems of interest are fundamentally nonlinear. Lots of biological systems of interest are fundamentally nonlinear. Okay, and recently, actually, I was just mentioning biological systems. There's been a lot of kind of an explosion of applications of control, and particularly of nonlinear control, to biological systems. Okay, so now, in some cases, a linear approximation is perfectly fine. Okay, so in other words, next time you board an airplane to go to Europe, don't panic, right? Because this, the airplane has been designed based on completely linear tools. So in several systems of interest, particular, at least until recently, large airliners and so on, and of course much simpler systems like simple motors where you don't try to get very high performance or something like this. In important classes of systems, linear approximation is fine. Okay, so some important classes of systems. So those are the ones we won't talk so much about, except to say, for instance, even in aircraft design today, you get more and more nonlinear tools. Now, to try and understand perhaps intuitively, the role of nonlinearity, we can think about some simple examples. So when I take things from the textbook, I'll put references. And so, if you think of the simplest linear system, perhaps you could think of, or one of the simplest, it could be a scalar system like this, right? X dot plus x equal u, right? Where u is the input and x is the state, right? The one-dimensional state. So it's a scalar system. And it's linear, right? So if you want to take kind of the simplest or one of the simplest possible nonlinear versions of it, well, you could think of x dot plus x squared equal u, but that's not a very good idea, or at least as a practical system, why is it not a very good idea? Or so it's going to be a so this system will be unstable, right? If you put u equals 0 and you start with a negative x, x will become more and more negative, right? So this system will, not be a nice stable system to play with. Okay, certainly not as a first toy example. Okay, so you understand this, right? If you put u equals 0, you get x dot equal minus x squared, right? So if you start with x negative, keeps going, right? Okay. So what could we think of? Well, maybe something like this. So let's use the more appropriate notations. Something like this. So I've replaced x by v. So what is this? Well, it's a very, very simplified motion of an underwater vehicle. Okay, or it could be a very simplified motion also of something with a parachute. Okay, so here you have a square drag law. Okay, so of course the real dynamics is much more complicated than that because it's fluids and and so on. But if we try to look for a very simple model, we could think of something like that. Okay, so it's from here to here, you've just added this quadratic term, and it has the right sign. Okay, so when v increases, it does try to slow it down. Okay, yes?
So why not x positive?
I'm sorry?
Why it doesn't go unstable with x positive, the middle x dot plus x?
Why does this? Well, for x positive, it will decrease. Okay, but it's not. It depends on the kind of system. This is. Also, the question is where, you have to think of a physical system that you're interested in that will look like this. Okay, these are much more common in some sense, right? Things with drag and so on. But it doesn't say. You could, of course, specialize this if you want. I'm just saying, we're trying to look for a nice, simple example, which is rather broad. Okay. Okay, so let's think about that, right? So let's think about this system. Okay. So it's scalar, it's nonlinear, and let's just wonder what happens when we do what we would do with a linear system. For instance, you give it a step input and see what happens. Okay. So let me still write this here, okay? So this is just scalar and nonlinear. Let's give it a step input. So this is time. The system is originally at rest, and we give it an input u. So u was originally 0, the system was at rest. We give it an input u, which is equal to 1, for, let's say, a duration of 5 seconds, and then we remove the input. Okay? So everybody sees what we're doing now. We're considering this system. Originally, v was 0. If it was an underwater vehicle, it means it was just sitting there. Okay. We apply some input. If it was an underwater vehicle, this would be some thrust from motors. Okay. So for instance, this would be thrust. We apply this input for 5 seconds, and then we remove it. Okay. So what will the system do? And again, if you prefer things about parachutes, it's fine too. You can think of it that way. Okay, so what will the velocity do? Originally, it was 0. We apply this input, so what will happen? Think of the physical system, and we will develop much more careful and detailed way of looking at these things, right? But for the moment, just think of the physical system, okay? You have this physical system of mass 1 with square drag, a thruster. Originally, it's at rest. You apply some thrust. What happens? Yeah? Something like that, right? So it does something like this, right? And it tends towards something, right? Tends towards a constant thrust, a constant speed, right? Where basically the square drag and this thrust exactly balance each other. Okay? And then, so we have this 5 seconds here, right? What happens after 5 seconds? You remove the thrust, right? So you're left with only the drag. Okay. So basically you go down, back to 0. Now, notice, and I could, you have a better drawing in the book, but the exact drawing in the book, but is the way the system is going up and it's going down, is it symmetric as it would be in a linear system, right? In a linear system, you would go up to a constant, and then when you go down, you're basically adding minus the input, right? And so you go down the same way, right? In this system, again, we're just trying to do the simplest non-trivial nonlinear system, right? In this system, as we remove the input, what happens? It goes down, but it doesn't go down the same way. Okay? Actually, it's going to be quite sluggish in this area. Okay? And intuitively, why is that? Again, we make much more precise statements about that. But intuitively, why is it that, in this area it has kind of fast behaviors, and in this area it's going to be very sluggish? Yeah, right. So you see, intuitively, again, we'll be much more precise than this. But of course, you could write this as absolute value of v times v, right? And view this as a damping coefficient. This is not quite correct, of course. We'll come back to that. But intuitively, you can say, well, I have velocity. Instead of having a damping of 1, I have a damping which is equal to velocity itself, right? So it means that, as I go in different areas of you know, how large velocity is, the damping, the apparent damping is going to be very different. Okay? Now, suppose I do the same experiment here. This drawing is not to scale, okay? But suppose I do the same experiment now, except instead of having a thrust, maximum thrust of 1, I put a maximum thrust of 10. Okay? So what happens? Well, I'm going to likely go through more of a velocity range, so the difference between going up and going down is going to be even more visible. Okay. Now, what will happen when I put this thrust of 10? Constant thrust of 10, the vehicle accelerates and then, you know, gets to a constant velocity. Equal to what? So if you're in linear systems, you have the final value theorem, but you know, in a sense, it's not very helpful because it assumes that you know that the system tends towards a final value, and if you know the system tends towards a final value, then you know it basically means that all its derivatives tend to 0, which means that it's very easy to compute that final value. Just put all the dots equal to 0. And you can do the same for nonlinear systems. You know, here you know that it will tend towards a final velocity. And of course, for this final velocity, you will always have final velocity, absolute value of final velocity is equal to u. Right? So we have this system here. We give it an input of 1. It behaves differently on the way up and on the way down. We give it an input of 10. It behaves even more differently, and the velocity at which its maximum velocity is what? Square root of 10, right? 3 point something. Okay. So again, this is not to scale. Here and then take it. Do something like this. Again, you have a much more precise drawing in the book. But the main point I was trying to make here was that, yeah, that velocity will be square root of 10, which is something like 3.3. So in other words, when you give it 10 times the input, it doesn't give you 10 times the response. Okay? So it means even if we go to this, which is basically the first non-trivial nonlinear system you can think of, right? All the reflexes you've acquired about linear systems don't work. Right? It doesn't behave on the way up the same way that goes on the way down, because on the way down is not the same thing as adding the response to minus u, right? Because you can't add responses. And if you scale the input, you don't scale the response. All right? And until reasonably recently, you had papers in distinguished journals which actually forgot about this in some way, not in such a trivial way, but looking, for instance, at robustness and say, consider a Bode plot, right, of something. If you consider a Bode plot, it means you're in the frequency domain. If you mean in the frequency domain, it means you're using a Fourier transform. And if using a Fourier transform, you assume something about linearity, basically. What Fourier transform does to convolution and so on, right? So of these reflexes and these tools, like the Fourier transform, completely disappear when we deal with nonlinear systems. Okay? What comes to the rescue, though, is that it kind of forces us very often to think more carefully about the physics of the system, which can only be a healthy thing. Okay? So very often, it's, you know, in a number of very practical cases, not going to be that hard to design nonlinear controllers, because you're not going to consider them as just mathematical equations. You really have to look deeply at the physics of the system. Okay? Questions about this? Okay. So this completes our coverage of chapters 1 and 2 of the book. So we're going to move to chapter 3, which is about a very fundamental tool in stability analysis, which is called Lyapunov theory. So, you know, the resonance stars in linear control are people like Kalman and Leuenberger, and in optimal control, people like Bellman. And in nonlinear control, nonlinear systems, you know, you have few names, but Lyapunov and Poincaré are probably the most obvious ones. So Lyapunov was a Russian mathematician who lived in the late 19th century and the beginning of the 20th century. He did many things. He was actually a student of Chebyshev, so he did actually many things in probability theory. And he's actually at the origin of the modern proof of the central limit theorem. In the process, it developed, you know, tools which are used in lots of other theorems and probabilities. And then later on, because at the time in Russia you did PhDs much later on. Later on, he worked on stability, okay, and what is known as Lyapunov theory. So it's Alexander Mikhailovich Lyapunov, and he apparently, when he got married, both he and his wife signed an agreement. I'm not sure if this is true, but signed an agreement saying that whoever would die first, the other one would kill himself or herself within a week. Anyway, so I'm not sure whether that's true, but what is a fact is that when Lyapunov's wife died, he was 61 and he killed himself. So, which is a sad thing for science. So, now before we go into Lyapunov theory, because in a sense, Lyapunov theory is really something which was done by a mathematician, but at the same time, as you'll see, it's something very fundamentally based on physical intuition. Okay, and that's all the elegance of it. You know, Lyapunov theory, in a sense, is one of the most elegant, or the basic theorem of Lyapunov, some of the most elegant theorems anywhere, right? Because the proofs are so simple in a sense and so powerful. But they relied very directly on physical intuition. So, but before we get into this, let's give a few definitions. So as I said, when we talk about nonlinear systems, here we'll be meaning systems defined by, for instance, nonlinear differential equations, where you have the state here, x, and a system like this, like x dot equal f of x, where f is, of course, nonlinear, is called autonomous. or time invariant because it's just f of x. It's not f of x and time. Okay? So, you know, if you assume something like this, assume I was holding really rigidly and I would let it go, right? If we assume, you know, there's not too much disturbance from the air, which could be time varying and so on, this would be a pretty good, you know, pretty good system to model as x dot equal f of x, okay? If you start, you know, making this like a wing and you start opening the doors and the windows and so on, that might look much more like something that might depend on time, okay? But, so these are called autonomous as opposed to systems where time appears explicitly on the right-hand side of the dynamics. These systems are creatively called non-autonomous or time varying. Okay. Now, these may represent either open loop or closed loop systems. Okay. So for instance, suppose you take this system and assume there's a motor at this hinge, okay, an actuator. And you're trying to control this system. When would you likely have an autonomous closed loop system? Right, so suppose we do a small variation, right, on the notation. So let's say x dot equal g of x and u, where u is an input. So the system is autonomous with respect to x, right, and then there's this input. Right? Now suppose you design a control law which is just u equal u of x. Right? So you take the system, g of x and u, and you design u equal u of x. Right? So now it gives you in closed loop x dot equal g of x u of x. And therefore the closed loop is autonomous. Right? So for instance, typically what kind of control problems would those be? If you had to take a guess for this system. Well, you know, systems where you want to go to a given position, you know, you want to go here. Okay, and stay there. All right? So here you would have an autonomous system. Now, when even with an autonomous system with respect to x and just u, you would have a non-autonomous closed loop. Well, if u was a function of x and time, for instance. Okay? So even if you start with an autonomous system, just with an input, if u is a function of x and time, then you see the closed loop system is going to be a function of x and time because of u. Right? And so the closed loop system will be non-autonomous. Okay? Now, when would you need to do something like this? When would you need to have u, which depends both on the state, let's say we measure the state, and on time? Yeah, if you have a trajectory tracking problem, right? You're not just going to go to 17 degrees, you're trying to have the thing draw something or follow some precise motion. Okay? Then you'll have the control input, which will have to depend on that desired trajectory. Okay, and therefore, whether the original system is autonomous or not with respect to x, right? The presence of this control input will make the closed loop system non-autonomous. Okay? So why do we make this distinction? Because, as I mentioned, these Lyapunov proofs, the basic Lyapunov proofs, are extremely simple and elegant, but they are different They're so simple and elegant that they are different in the autonomous and non-autonomous case. All right? In the autonomous case, you have really a very simple, beautiful interplay between geometry and dynamics. Okay. In the non-autonomous case, you'll have to be a little more careful. Okay? So that's why we make this distinction. So now, if we had a linear system, right, and we worry about its stability, let me just take a short break. Forgot to give you those. If you could just fill those, just put your name, which course you are, which year you are, your email, any previous course you may have had in control or closely related like robotics, okay, and whether you planning to take this course as for credit or as a listener. It doesn't mean you're committing yourself to that. It's just what are your plans. Okay. Okay, so let's get back to this, right? We have, in the linear system, first thing you generally wonder is, where its equilibrium point. Typically you take it at 0, but it could be somewhere else, okay? So here, you can think as well of questions of equilibrium. Now, in the rest of this lecture, and until further notice, we're going to consider autonomous systems, okay? So we're going to consider systems of the form x dot equal f of x. So, what do we mean by an equilibrium? Well, kind of a natural definition is to say a state, a point in the state space, such that if you start there, you stay there. Okay? So that's what an equilibrium is, right? So it's a point in the state space, a particular state, such that if you start there, then you stay there. Okay? So given this dynamics, x dot equal f of x, which says the change of the state x is equal to f times the value of the state, how can we find an equilibrium point? Well, it simply says if we start there, we stay there, right? So if we start there, then x dot should be 0. All right? So an equilibrium point says it's going to be a point f, let's call it f EQ, right? Or whatever you want to call it, right? Such that f of that state, f at that point is 0. All right? Now, if you think about it, and certainly when people were starting to play with these things, people like Lyapunov and Poincaré and so on, incidentally, it took a lot of time for Lyapunov's work, which is so fundamental, to be translated in English. Okay? It was translated in French in the early 20th century at the request of Poincaré, right? And then it was translated in English much later in the late 40s. Okay? But at the time, just solving this equation was a non-trivial thing. You couldn't just log in, right? Just think of a nonlinear f, right? Just solving this equation was not a trivial thing. And of course, this equation may have multiple solutions, right? Now, so we'll do this just a little more precisely, but think again about this system. Okay, no actuator, just, a hinge. Okay. So, can you give me an equilibrium point? Well, here, right? as you say. So if you think of this angle, right, so theta equals 0, theta dot equals 0, okay? Can you give me another? Well, theta equals 2 pi, theta dot equals 0. Can you give me another? Well, theta equals 3 pi, and so on, and so on for the rest of the lecture. Can you give me something a little more exotic? Yes, so this one, right? Theta equals pi, theta dot equals 0. And of course, theta equals 3 pi, theta dot equals 0. Okay? So you see, for this system, so we don't assume anything small, right? For this system, you have two infinities of equilibria, right? Here and there, right? And we're not there yet, but as you can guess, there'll be one of the differences between these two infinities, which will be stability, right? This will probably be something kind of stable in ways we'll define, and this will probably be something kind of unstable, right? You see also that when we did this, we already took a model where things were reasonably simple, right? If you assume there's something like stiction, you might very well be stuck here. So in other words, you could have a whole region, right, which is just full of equilibria. Okay, or you could be stuck here. Okay? All right, so just as a little exercise, let's do this a little more explicitly. So we have a pendulum, right? Let's already model it just, with a radius and a mass and an angle theta. So incidentally, this is example 3.1. So what's the equation of this system? So it's F equal ma, right? So there's an inertia, which is mr squared, theta double dot. There is a gravity torque, which is mgr times what? Times sine theta, right? The gravity torque is 0 when theta equals 0. But equal to 0, and we'll add in some damping b theta dot. Okay. Okay. So, if we wanted to put this system in state space form, what could we pick as a state? So not a unique solution, of course, but what's a very simple thing to pick as a state? Right, so we could pick x1 equal theta and x2 equal theta dot, right? Now we could very well pick x1 equal theta and x2 equal theta plus 3 theta dot, right? But it's not as easy. So we can just pick it this way. So what are the state equations? So in other words, we have this equation, which is F equal ma, right? What are the state equations corresponding to F equal ma? Well, first equation x1 dot equal x2. Right. Second equation, x2 dot equal, well, you have to put it together, okay? It gives you minus b over mr square x2, and then minus g over r sine theta, which is the same thing as sine x1. So these are the state equations. Okay? So in other words, this is f of x, right? Right? And this is, of course, x dot. Okay. So how do we find equilibria? Equilibria, well, we just look for f of x equals 0. Okay. So f of x equals 0 is equivalent to x2 equals 0 for the first one. And then this whole term equals 0, but we know that x2 is 0. So it's simply No, yeah, right. So it's simply sine x1 equals 0, right? Right? So we just solve this algebra, right? It says x2 equals 0, and then the second term is 0 too, but x2 is 0, so it's just say this term is 0. Sine x1 is 0. So we find again, you know, what I was saying before, right? Sine x1 equals 0, we have things at 0 and we have things at pi, all of them modulo 2 pi. All right, so we find exactly what we had before. Okay, questions about this? All right, don't hesitate, right? It's much easier to ask directly than to later ask a friend who missed it too because it was not well explained. Okay, so if there's any question, just ask. Okay. Yes.
I know this sounds weird, but if you have a time, right, like for the Donald-Trump system,
yeah,
why can't you just consider time as being a state?
So you could define t dot equal 1, right? But it's a very special kind of state. It doesn't start anywhere and so on. You know, so there are some theorems where you can play with that, okay? But it's generally not what you do. Okay. So before we go any further, let me apologize to half of you, and probably to the other half as well for the converse reason. We use this notation here, which I said was equivalent, okay? So statistically, half of you have seen these kinds of notations since kindergarten, and the other half have never seen them, okay? So let me just recall some very, very basic mathematical notation, which are just shorthand, okay? So this means for any, right? So people come from abroad, especially say, well, wow, I'm coming to MIT and explaining this in a graduate course. Anyway, but this is just shorthand, okay? So this means there exists at least one, right? What else? This means in the set, this means implies that. And if it implies in both ways, it means it's equivalent to. And so these are just mathematical shorthands. Okay. Now, so as we said, now that we have the equilibria of a system, we have to differentiate, what's going on here from what's going on there. Okay, and it's likely has to do with notions of stability. Okay. Now, we're going to give a number of notions of stability, and at the beginning they might sound a little technical. You might wonder, why are we, splitting hairs like this? But as you'll see, they'll correspond to very practical engineering concerns. Okay, so it might look at the beginning a little technical, but they'll actually be they correspond to real questions. Okay. In this course, we try as much as possible not to do gratuitous mathematics, so it doesn't. Okay, so let's consider. So we're looking at notions of stability, okay, concepts of stability. That's an orange stroke somewhere. So it's section 3.2. And this is all from Lyapunov theory, right? So this was all in Lyapunov's work. So there's one first notion which is called just stability. And remember we said that if we just look at this equation, f of x equilibrium equals 0, in general it has multiple solutions, right? And we saw here the system. So an example, right? So it means that when we talk about stability, we're not going to, if I tell you is this system stable, well, you might say, well, it doesn't explode, but right, I mean, the question is more, is this equilibrium stable, right? So in general, in a nonlinear system, a nonlinear autonomous system, unless you have a single equilibrium, we're not going to talk about the stability of the system because that's ambiguous. We're going to talk about the stability of an equilibrium. Okay? So it's concepts of stability of a specific equilibrium. And just for notational simplicity, we don't really have to, but we'll assume this equilibrium is 0. Okay? I'm saying it's notational simplicity because if this equilibrium is 17 and minus 6, we can just shift the origin of the state space, right? Subtract this from the definition of the state, and then in a new state, the equilibrium is 0. All right, so this is completely without loss of generality, okay? We'll do other things which are less obviously without loss of generality, okay? But we'll use this without loss of generality. Okay, it just means if it's not 0, then you just put the origin of the state space there. Okay. So there's something which is called stability, or stability in the sense of Lyapunov. And it says, okay, so you have your equilibrium here. This equilibrium is stable if I pick some big ball around this equilibrium. So I pick an arbitrary ball of radius r. So remember, a ball centered at x equals 0 of radius r just means there's all the sets of points x such that norm of x is strictly less than r. Okay. So with a better drawing, this would look more like a circle, right? And the ball is this entire region, within this red shell. Okay. So it's a set of all x's such that norm of x is less than r. Incidentally, here we use the Euclidean norm. We'll see in the homework you can use other norms, and then the balls look different. Okay, but the principle is still the same. So stability in the sense of Lyapunov says, if I pick a ball of radius r is arbitrary, okay, there always exists a smaller ball of radius small r. That's better. There always exists a smaller ball of radius small r such that whenever I start in the small ball, any trajectory that starts in the small ball may go in and out, but it never gets out of the big ball. All right, so I have my equilibrium of interest. I take a ball around it any way I want it, and in particular as small as I want it. I can always guarantee that I stay in this ball of radius big R by starting close enough to the equilibrium point. All right? So it says I can always maintain my system in a certain region, however small I want it. Okay, big R, you could make it as small as you want, by starting even closer to the equilibrium point. All right? So it's a sort of kind of guaranteed boundedness, okay, for people very fluent in mathematics. It's a form of continuity as well. So what does it say? It says you can maintain your system in a given region of the state space, okay, by starting close enough to the equilibrium. Now, why is that important? Well, because of course you might want your system to be there, okay, and make sure it stays there, okay. But also that region may be the region where the model is valid, right? If you take something like Concorde, which was one of the few examples where technology regressed, we don't have transatlantic supersonic passenger aircraft anymore, right? But if you take something like Concorde, right, it was a supersonic aircraft, but of course, it wasn't supersonic from the airport, right? So you had to go subsonic, take off, and so on, right? And then go supersonic. And the equations for supersonic and subsonic are completely different, right? So when you want to, let's say, you do something in a certain set of equations, you want to make sure at least the set of equations remains valid, right? You don't want the thing to go into supersonic and back in your calculations because the real plane won't do that. Okay. You had a question?
Yes, the inequalities are strictly less than, right? What happens?
Yeah, it's just a definition. Just
Same for small r. So I have
yes, the same for small r, yeah. Absolutely. Yeah. So, absolutely. So that's just what it means, right? So it's stability in the sense of Lyapunov. And so just for simple practice, right, how would we write it using these gadgets called quantifiers, right? It says for any r, okay? So I said there exists a smaller r. Why does this have to be smaller? Because of course this couldn't be true if r was bigger, right? You wouldn't stay in the big R region. So it's thematically smaller, but you don't have to put it in the definition. Okay? So there exists a small r such that if x at time t equals 0 is less than small r, then x at time t remains less than big R for all future time, meaning for any t. Okay? So for any capital R, there exists a small r such that if initially you're in the small ball, then you never get out of the big ball. Yes?
Why do we need this small r? Couldn't we just say if we start somewhere inside the big R, then we stay inside the big R?
Because that would be a much stronger condition, right? Suppose you start here, right? You want to say, well, you know, there's a wall, right? But maybe there isn't, right? So it would be, well, you could define something like that, but it would probably be too strong a condition for most applications, right? And again, for those of you the mathematically inclined view, you can see so it's also a continuity condition, right? It has to do with continuity of where you end up as a function of the initial conditions. Okay. So that's one first definition, stability. Oh, maybe there actually. So, second definition, asymptotic stability. So asymptotic stability says that of an equilibrium, right, is that this equilibrium is stable in the sense we just defined. And there exists some number, let's call it R0, which doesn't depend on some big R, it's just a number, maybe 17, okay? There exists some R0 such that if fx of t equals 0 is less than R0, then x of t tends to 0, the equilibrium, as t tends to infinity. Okay? So it says, maybe I'll just redraw it not to, well, you have this condition, right? And then you have an extra condition which says there exists some R0 around this equilibrium point, okay, such that whenever you start in a ball of that ball of radius R0, not only you don't get out of balls you might have found and so on, but you do end up at 0. Okay, so it's two conditions. First, it's stable in the sense we just defined. Two, there exists a small ball Okay, and of course all the smaller ones work too, but there exists a small bolt such that if you start in there, you get back to 0. Okay? Now, so this is two different things, right? What is this extra condition says? It says that not only you can bound the system any way you want, right? But actually, if you start it close enough, it actually does something. It goes somewhere, right? Right? So it's not just preventing it from, getting away in ways that you can control. Okay, so making it stay into as small regions as you want, but also making sure that if you start it close enough to the equilibrium, it does go back there. Okay. Now you might ask, so that's Lyapunov's definition, right? You might ask, why didn't he jump directly to the second condition? You know, why did he bother to say my definition of stability and then this? Okay. And of course, at the time he wasn't thinking about supersonic aircraft, right? But it's basically the reason I was mentioning before. Okay. In other words, if you didn't have the first condition, you only had the second condition. There exists some finite bolts that if you start there, you end up at 0. It could be possible that, depending on your initial conditions in there, this trajectory gets out of regions, for instance, where the model is valid. Right? It doesn't say it stays inside the green ball, right? It says it ends up at 0, but in the process it could go way out and get back. Right? So that's why this explicit condition of stability was kept in the asymptotic stability definition. Okay. Now, if R0 is actually infinity, and with a slight abuse of notation, namely, if starting anywhere, you go back to 0, okay, then this is called global asymptotic stability. Okay, and then of course, if you want to be consistent, you can first call the first one just local asymptotic stability. Okay. But so if it's true that not only you can bound the system arbitrarily, as in just stability, but also starting anywhere, you end up at 0, then you can talk about global asymptotic stability. Okay? And in this case, we can actually say, if we want, that the system is globally asymptotically stable. Remember we said, be careful, you might have several equilibria in any shape or form and so on, all regions of equilibria and so on. So we talk about stability with respect to particular equilibria, which we call x equals 0. However, if we have global asymptotic stability, we know that starting anywhere, we end up at this equilibrium, and therefore, there are no other equilibria. Right? Starting anywhere, you end up at this equilibrium, right? If something else was an equilibrium, this was the equilibrium, something else was an equilibrium, starting there, you would stay there, right? Because it's an equilibrium. But starting there, you go back there, okay? So, in the case of global asymptotic stability, we can talk, of course, about global asymptotic stability of equilibrium, but it's okay to talk about global asymptotic stability of the system because there can only be one equilibrium. Okay. So we have 3 versions so far. stability, which has to do with making sure we maintain the system in the region we want. Asymptotic stability, which says not only we do that, but it goes somewhere, it does something. And global asymptotic stability says not only we do that, but it goes somewhere starting anywhere. Okay. All right. So now let's talk about one last form of stability, which is exponential stability. Of a particular equilibrium point x equals 0. And which says, starting in some ball of radius r0, there exist two positive numbers, alpha and lambda, such that x of t for all future times remains less than whatever it was at t equals 0 times perhaps some scaling factor alpha times e to the minus lambda t. Okay. Okay. This scaling factor, of course, alpha, we said larger positive, but you can see actually it has to be larger than 1, larger or equal to 1, right? Because if you apply this at t equals 0, it has to work. Okay, so it's really larger or equal to 1. It's a scaling factor, which says, you know, it could start in some ball and then get out of there. Okay, and then e to the minus lambda t. All right. And so this is local, and of course you have a global version in the case that R0 is equal to infinity, namely starting anywhere, you have this verified. So for all trajectories, so there exists alpha and lambda, such that all trajectories starting in this ball R0, this is true. And if R0 happens to be infinity, then of course it's global. And you can show, you'll see this in the homework, that in the case of exponential stability, we don't have to worry about the fact we should explicitly ask for stability because it will take care of itself. So that's, here we don't have to explicitly ask for stability. Now, so what does exponential stability imply? It says not only you go somewhere, but you have a time constant. Okay? You go somewhere and you know roughly how long it takes. Okay, because you can do the same approximations on, you know, how small an exponential gets, you know, within a few 1 over lambdas that you do in linear control. Right, so it's so first case stability, you know, bounding things arbitrarily. Second case asymptotic, going somewhere, local or global. and then two other forms, exponential local, exponential global. All right? Notice as a remark, if you write alpha in the form, so alpha is some number larger than 1, okay? So you can write it as e to the lambda t0, which defines the number t0, okay? Then you can see that alpha e to the minus lambda t is the same thing as alpha e to the minus lambda t minus t0. Okay, so in other words, if you define t0 by tau 0 by this equation, actually I'm defining, tau 0, sorry. If you define tau 0 by this equation, e to the lambda tau 0 equal alpha, right? So it gives you, you can solve this easily. Then alpha e to the minus lambda t is equal to alpha e to the minus lambda t minus tau 0. Okay.
What if alpha is still there?
Oh, sorry. It shouldn't be. Thank you. It's equal to that. Yeah. And so what does it mean? It means that basically you get this exponential convergence without an alpha, right? But after tau 0. Right? So in other words, if you're looking for ballpark estimates of how long does it take to converge, well, it's tau 0 plus 3 over lambda, or tau 0 plus 5 over lambda. Okay? It's the alpha is basically some extra delay you have to wait until you have this pure exponential, okay, of gain 1. All right? So this is an extra delay if you want. Okay? So by now, we have 5 versions of stability, right? Which corresponds, as we saw, to very practical concerns. Being able to arbitrarily bound the system around an equilibrium by starting close enough to it. Being able not only do that, but actually, if we start really close, to go back to the equilibrium. Being able perhaps to guarantee this property starting anywhere. That's global asymptotic stability. Being able to know a time constant, either locally or globally. Okay? So we have by now 5, and I reassure you that's it, definition of stabilities. Definition of stability. Why, unless you took a course in nonlinear control, haven't you heard about this before? Bad teachers? Why are we talking about 5 forms of stability? While, in the linear case, it's stable or unstable. Perhaps we say strictly stable or marginally stable, but basically it's stable or unstable, right?
We always close to the equilibrium, right?
What?
The linearity is valid only around the equilibrium.
Yeah, but so suppose we have a real linear system, x dot equal ax.
Linear systems with exponential stability.
Yeah, so in a linear system, in a strictly speaking linear system, right? If the system is strictly stable, it's globally exponentially stable, right? Exponentially because you have poles and so on, right? And globally, because of course it's a linear system, it does, so the linear system x dot equal ax doesn't say if x is less than 17, right? So it's globally. So the reason you don't hear about these subtleties which correspond to very practical concern, does it do something? How long does it take? Where can I start it and make sure it does something? Okay. Of course, as applied to a closed loop system, right? You haven't heard about this before because in the linear case, it's kind of black and white, right? Either if it's strictly stable, then it's globally exponentially stable, right? So in the linear case, you go directly to the strongest case, right? Globally exponentially stable. But of course, in the nonlinear case, you have to be careful about what you do. So what we'll do next time, these are definitions, okay? And next time we'll show some main theorems of Lyapunov, particularly in the stability and the asymptotic stability case, local and global, which tell us under which condition these properties are verified. And as I said, it's very elegant, very simple proofs, okay? That are due to Lyapunov. See you next time.